All right, so we talked about limits and the behavior of a function. So how, as you get closer and closer to a certain x value, what y value are you approaching? We talked about convergent behavior and divergent behavior. Now, the first place that limits apply themselves is this thing called a derivative. Now, I'm going to be really brief here on this, is that a derivative is a fancy term for slope. And if you ever notice in algebra, we talk about slope a lot when we're dealing with linear functions, y equals mx plus b. We talk about slope all the freaking time, and then the minute we put a little 2 on the exponent, we never talk about slope again. All right? And the reason for that is because the slope of a linear function is constant. It's always the same increasing or decreasing value. But the minute you get a parabola or you get a cubic or a square root function, all of a sudden, where you are, the slope could be different. Now, calculus is the study of things in flux as functions change. What's their behavior? What are they going towards? And the first place that limits apply themselves is derivatives. Now, derivatives is a fancy word for slope. Now, if you think about a function, it depends what x value you plug in to get your y value. Now, a derivative is that same concept, except the derivative describes the slope, the rate of change. Depending on your x value, what is the rate of change of the function? And a parabola, the rate of change is different depending on where you are. So the derivative is a function that describes the slope. Okay? Now the first rule we have, we're going to skip, unfortunately, this pains me, we're going to skip this thing called difference quotients. We're just going to go right to the derivative rules. If we were in class right now, I would blow your minds with this difference quotient idea, but unfortunately, I'm going to tell you to go and look at YouTube or something else because I just can't do it justice in these videos. Derivatives, the power rule. All right, this is the first rule that we look at, and it's a way of quickly getting derivative functions. So you have f of x equals ax to the power of n. Now, a is just a coefficient. It's the leading coefficient. N is your exponent. That is a natural number. It could be positive, it could be negative, it could be 0, it could be a fraction. All right, it's just a number. Now, f of x changes to f prime of x. F prime of x. The prime means the derivative. Now, what happens is, now there's an n out in front of the a. So this n, it comes down and multiplies by that coefficient. You still have x, and then your exponent decreases by 1. So your new exponent is the previous exponent minus 1. So n comes down, multiplies into a, n decreases by 1. So exponent comes down, decrease exponent by 1. Exponent comes down, decrease exponent by 1. Now the sum and difference rule, this here, d dx, the derivative with respect to x. The derivative with respect to x. d dx of f of x plus minus g of x. Let's say you got a couple of different functions lined up with pluses and minuses in between them. Well, the sum and difference rule says this is actually pretty simple to take care of. Just take the derivative of the first piece, f prime of x, take the derivative of the second piece, g prime of x, and then plus minus, whatever needs to go in between them goes in between them. All right? So this power rule is for powers, for exponents. All right? That's when you can use this rule. So example 1, f of x equals 4x cubed minus 3x squared plus 7x plus 9. Now we have a minus, a plus, so we're going to use the sum and difference rule. And then each one of these pieces is a power with an exponent. So we're going to use the power rule. So you're going to use multiple rules. They kind of stack up on each other. So f prime of x. So power rule, bring the exponent down, 3 times 4 gives you 12. Decrease your exponent by 1. 3 minus 1 is 2. Next, bring the exponent down. 2 times 3, that'll give us a negative 6. Decrease the exponent by 1. 2 minus 1, let's just call it 1. 6x to the first. We won't even write it. Now this right here, okay, 7x to the first. let's do the same rule. Bring your exponent down. 1 times 7 is 7. And then decrease your exponent by 1. So we have x to the 0 power. Now anything to the 0 power is 1. So this x to the 0 is just a 1. We don't need to write that. So it's just 7. Now this 9. Okay, let's think about this. Derivatives talk about the slope, the rate of change, how something is changing. Another word for 9 or a number is a constant. Think to yourself, what is the rate of change of a constant? How is a constant object changing? Well, by definition, it's not. Okay, there is no rate of change of a constant number. So this 9 cancels out. It's no longer a part of the derivative function. Now let's use the power rule just to kind of show you that this does work. Technically, this 9 is 9x to the 0. Well, let's go ahead and bring this 0 down. 0 times 9, well, 0 times 9 cancels out. So you see it works with the power rule as well. Think about it holistically. How does a constant value change? It doesn't. Use the power rule, it cancels out, it does not affect our rate of change. So we have our derivative function. Easy peasy mac and cheesy, all right? Now let's look at how this can be a little different. Now let's throw some radical symbols in there, and let's throw some x in the denominators into there. Now sometimes these problems require a rewrite, okay? The power rule only works if you have a power, an exponent. So let's go ahead and rewrite all of these terms with a exponent and no fractions involved. So square root of x, to rewrite that with a power, that's x to the 1/2. The cube root of x squared, to rewrite that as a power, that is x to the 2/3. All right, the exponent becomes your numerator, your index becomes your denominator. Just like over here, technically there's a 2 and a 1. Exponent becomes your numerator, index becomes your denominator. This 1 over x to the 3rd. Now, we know how to move objects around inside of a fraction. You move it from the bottom to the top, or the bottom to the top, or the top to the bottom, just by making the exponent negative. So this x to the 3rd in the denominator, we can rewrite that as 1x to the negative 3rd. And then over here, this minus 5 over x squared. Well, we have the minus 5, bring the x squared up, and it's x to the negative 2. So now everything is written as a power with those numeric exponents. Now we can use the power rule along with our sum and difference rule. So this 1/2, bring it down, 1/2 x, decrease that exponent by 1. 1/2 minus 1 gives you a negative 1/2. Next one, x to the 2/3, bring that 2/3 down, decrease your exponent by 1. 2/3 minus 1 is negative 1/3. Now this next one, x to the negative 3rd. We'll bring that negative 3 down. So minus 3x. Decrease your exponent by 1. Negative 3 minus 1. Negative 4. And lastly, this negative 5x to the negative 2. Bring the negative 2 down. Negative 5 times negative 2 gives you positive 10. Decrease the exponent by 1. Negative 2 minus 1. Negative 3. So we have our derivative. Now, we could clean this up a little bit if we wanted to. I'll kind of show you briefly. All right. This x to the negative 1/2, we could move it back down to the denominator. So it become a positive 1/2 exponent. And then the 1/2 exponent gives us a square root. So 1 over 2 root x. Same thing here. We could take this negative 1/3, x to the negative 1/3, bring it down into the denominator. and then turn it back into a radical as a cube root. This x to the negative 4, we could take that back down to the denominator, make it positive. And the x to the negative 3. We can put that in the denominator and make that positive as well. So either of these can be acceptable. All right, either one. Lastly, a little bit more complicated of a fraction. Now another rewrite. In algebra, we do a whole lot of this kind of stuff. All right, can you see this? All right, we're good. 1/2 plus 4/2. 1/2 plus 4/2 gives you 5/2. We do a lot of putting together in algebra. Well, this is an equation. That's a biconditional statement. It can work both ways. So you can also take things apart. All right? So to rewrite this, we can say this 3x squared. Let's put that over 2x. And this negative 5, let's put that over 2x. And now we can do a little bit of simplifying, rewriting, okay? We have some x's we can cancel out here. We have a x in the denominator we want to take care of. So let's cancel those x's out there. And this x with a positive 1 exponent, let's move it up. So our rewrite would be 3 over 2x minus 5 over 2 x to the negative 1. So if we go ahead and take our derivative here, so we have f prime of x. So this exponent of positive 1 here, let's bring that down. 1 times 3 over 2 is 3 over 2. 1 minus 1 gives you x to the 0, so the x term cancels out. And then this negative 1, let's multiply that down, becomes a positive 5 over 2. Decrease the exponent by 1, giving you x to the negative 2. And if you want, you could take that x to the negative 2, move it back down to the denominator. All right, so there we go. Power rule, sum and difference rule, kind of a bunch of different examples of how that can play out.